Hey guys, welcome to another video. So today we continue on with the topic of rates of change as part of the year 11, year 12 advanced syllabus. So last video, we basically introduced the concept, right? And the method on how to approach the rates of change questions, where just be absolutely clear, whenever we talk about rate in this topic, we use the calculus concept where it's, notational, it's D something, whatever you're changing in, over dt. Whenever you see dt, change in time, it's a rate. Now, last week I mentioned there were the three key shapes: the sphere, the cone, and the cube, as the three common shapes that you'll see in this topic. Today, we're going to bring forward some past paper questions that explores those. The last past paper question is a nice one, nothing to do with the three solids that we're talking about, but it does link on with the next video, where there is a method called implicit differentiation, which I believe a lot of students, a lot of teachers use as part of the extension 1 syllabus. Some teachers don't do it at all, but it's a nice little technique on how to differentiate implicitly to do questions a bit faster. So let's go through it. There should be 4 questions I'm going to cover today. A good place to begin is last week's, last lesson's theory, which covers now, and just to be upfront with you, there was a formula error that I put in, and I'll do it in red this time around, where I think I put it in the comment section as well. The volume of a cone is a third pi r squared h. I've got the h there, but I'm sure you guys all picked that up. So with that in mind, those three shapes there are classics. Let's explore some examples, some past paper examples with those in them. And also, just like I said before, whenever we talk about a rate in this topic, we're going to use the derivative of whatever variable we're changing in. Changing p is dp over dt. So without further ado, let's hit up some past paper questions. So also, before I begin, if you haven't subscribed to the channel, please do so. Helps with the search algorithm in YouTube, and like the videos and tell your friends. So let's do it. So I'll start with a question from Barker, 2011. Now, this question is, it looks quite simplistic, but it's worth 3 marks, right? Where it's a little bit more, I guess, involved than the last ones that we saw relating to a sphere. So let's read through this, right? So the volume of a sphere. So once again, volume, right? We know, generally speaking, the questions deal with either volume or surface area. In this question, it deals with both, right? It's nice. So the volume is increasing at a rate of 5 centimeters per second. At what rate? So I'll highlight in green what we have to find is the surface area increasing at, and given when the radius is 20. So we have 5 centimeters cubed per second. So that guy there is dv on dt, right? The change in volume over time. So that's 5 positive, right? It's given that r equals to 20. And in this question, they're asking us to find the change, also the rate of change in the surface area. So dA on dt, right? So we all know that volume of a sphere, right, is 4 on 3 pi r cubed, right? We're dealing with volume, we need this formula. We also know that the surface area is 4 pi r squared. I always ask my students, put down the formulas and go from there, right? Now, if we go back to rates of change, so I want the rate of change of v. I know that using the chain rule, I'm going to differentiate, bring down the 3, right? The 3 comes down and multiplies with this guy, right? So then the 3 and the third cancels out, so it becomes 4 pi r squared, right? That's the derivative. Now, I said to you last week, is it a coincidence that the derivative of the volume is equal to surface area? Don't know. Doesn't sound like a coincidence. Maybe you guys can tell me the theory behind it. Now, because I am differentiating with respect to time, and the variable at play here is r, I then need to multiply this by dr on dt, right? Yeah, chain rule. Now, you can see in the 2 blue things that I've been given, dv dt and r, there's nothing here that tells me that has a dr dt, right? That is not something that's given or talked about in the question. That's cool, right? So this is what I'm going to do. I've got the value of r, right? I'm going to sub in 20 squared into here, right? I've got the value of a dv dt, that is 5. Now, so this is the play. We are going to sub the 5 and the 20 squared in, and then make dr dt the subject. I reckon I'm going to need it when I find dA dt on this side. So pause right there on this side. Right? I'm going to sub in the blue, make red the subject. Perfect. Let's skip over to the area where I'm going to differentiate with respect to time. Bring down the 2, right? The 2 comes down and multiplies with the 4. You get 8 pi r multiplied by dr dt because of the chain rule. You can see here, guys, this is what I want, right? This is the question. On this side, I can sub in values of r, right? That is 20 in this question. Now, also, this dr dt is what I'm going to make the subject over here and then sub in. So you can see green is going to equal to 8 pi r, which is 20, multiplied by whatever red expression I get over here. Yeah. So this question is nice because you got volume, you got surface area, right? And together, because they're giving me change in volume and they want change in area, what isn't explicitly told is that I need to make the RDT the subject on this side, on the left-hand side, and then sub it into the right. Yeah. So in this question, let's carry that forward. So we're going to just sub in the blue on the left, right? Feels like we're doing two things at once, but that's fine. We are, right? Just so I can show you the linkage, right? Now, if I divide dA dt over to the other side, I won't simplify it yet. It really doesn't matter. So 4 times that, let's just leave it there for now, right? Guys, this is my, sorry, I wrote dA. Silly, should be dr, right? Little typos on that. Hopefully you guys are fine with the concept and excuse the little silly errors bound to happen. Now that's red, right? So both this guy, I'm going to sub this guy into here, plug that expression into here, and you should get therefore green, which is dA dt equals 8 times pi times 20, then times 5. Now I like this because the pi's cancel out, right? 5 pi on 20 squared. What goes here? The pi's gone. One of the 20s are gone. 8 and the 4 goes to 2. 2 and the 10. 10. 2. Ooh, it's a half. Perfect. Everything just sort of cancelled out therefore, right? Therefore, the change in surface area over time is 2 centimeters per second and units, no, centimeters squared per second. It's not even 2, right? Half. Come on. Perfect. That's better. How's that? So this question is nice because last week we either dealt with volume or surface area. This one deals with both, right? And the implicit thing there is you got to make dr dt the subject. Guys, that question there is from Barker. So many schools would have a question like this. It's in so many textbooks. Make sure you can do it when they combine volume and surface area. Let's do another one. Now, next question is from King Koppel, right? I can't emphasize how common this question is now. This question, we did it last week, very similar, different numbers, I believe. Same concept though, same concept. Now, I believe last week, correct me if I'm wrong, let me just quickly check. I think when we did it, I might have made a different letter the subject. Yeah, so this one is going to have H as a subject, while, because we're doing the rate at which the height's changing. Well, last time was the rate of radius, so slightly different, right? So it's good. Sorry, let's go through this. So shows a conical drinking cup at 12 meters high. So that's given in the diagram. I don't need to do anything there. The cup is filled with water at a rate. Now, the units in this rate gives it away that it's changing. Can you see 2 centimeters cubed, right? So that's dV dt is 2 centimeters cubed, right? Yeah, so that's given there. The height of the water T is at T seconds is H and R, so nothing there is fancy. All right, show that this happens. Perfect. Okay, I need to show that. Find the rate at which the height, right, is increasing. So they want me to find dH dt. For those that had just watched my last video, the same question here, I found dr dt, right? Slight differences, right? Subtle. Now, and they tell you when the height of the water is 8 centimeters. So they gave me here H equals 8. So it doesn't matter whether you find R or H, right? The key thing, if you really are on top of your game, you know this relationship here, right? If they want me to make H the subject, which is what I did last time, they'll tell me to find a rate of change of R. In this case, they won't want me to find DHDT. They're making R the subject. It all makes sense, right? And I'll show you what I mean when I do it. So part one. Part one, to show that a relationship, because now why, right? If you understand this concept, it's all to do with the volume of a cone. The formula that I inadvertently got wrong. Volume is a third pi r squared h. Now, the beauty about this formula and what makes it confusing for a lot of people, right? This formula for a cone has two variables on the right. There's v on the left, but on the right there's r and there's h. Yeah. Now, it's very hard to do rates of change when there's two variables on the right. So what do? They give you a relationship, in this case, in the form of similar triangles. They give you a relationship to find r in terms of h, and then you sub a quarter h into r. And then you only get h's as your volume, right? That's important. They always do that. They always do that. Whenever you got two letters, they always say so. In this thing here, so like I said, it's all to do with similar triangles in this diagram. So guys, you know what? I'm gonna take that triangle here. So using similar triangles, right? We have R here, H here. It's similar because of the right angle and the common angle, right? So you don't really need, it's implied, right? Yeah, the beauty about this is implied. We don't really need it. We just use it. Right? That's 12. So I always say to my class, small on big equals to small on big, right? And so therefore we have R on 3 equals to H on 12. They want to, now last week we made H subject. This week we're going to make R the subject, right? Times a 3 up. And you get what, yeah, you can easily go to a quarter H, which is exactly what I want. That was 1 mark, piece of cake. Now, what's the purpose? The purpose is to plug this guy into R here and then get an expression for the volume in terms of H, right? So let's do that for part 2. So volume used to be a third pi r squared H, right? So let's plug all this guy, whoops, into here, right? And then I get third pi a quarter H squared times H. Now, what am I trying to get to here? What's the biggest concept is on the right-hand side now, with R being replaced with an expression of H, I only have H's, right? As a variable, pi is constant, yeah? So you get volume equals to a third, now expand that as what, 16, so 48. So it'd be 1 on 48 pi H cubed, right? Perfect. That is the expression that I'm going to differentiate with respect to T, right? So let's do this. Once you get that, how much space do I have left? Oh, heaps. All right, cool. dv dt, right, bring down 3, becomes 1 on 16 pi h squared, because we're differentiating with respect to time. I have to multiply this by dh dt. Perfect. Now, this then tells me I've got an expression. Oh, sorry, I've got an input for that. dv dt, what's that? 2. Right, in the question there, it's up here, right? 2. The change in volume over time is 2. I've got a value for h at this point, which is 8. The HDT is the thing that I need to find in the question. So this one's question mark, sub blue in, make green subject, piece of cake. So let's do that. Let's see what we get. That's the next question. Don't want to go there yet. 2 equals to 1 on 16 times pi times 8 squared times dh dt. Therefore now, let's see, at 64 on 16 is 4. So once again, half. So 1 on 2 pi. Does that feel right? 1 on 2 pi. Therefore, right, dh dt. So we're making this guy the subject, right? So then if you bring everything over, it should be 1 on 2 pi units. What is it? Centimeters per second. And that is my answer. How's that? Guys, the cone question, make sure you can do it, right? Super important. super, super important. Yep. In this case, just be on top of your game when it comes to which letter you're making the subject, with the purpose of subbing it in to the red formula up there where there's R and H. So you only get one letter, one variable on the right-hand side. All right, guys. Next question. Now, this question, it's getting more and more popular, actually. I've seen it, I think it's because in the new textbook, in new Cambridge textbooks, I have this, right? Where previously in the rate of change question, there really wasn't that many questions that looked like this. Although saying that though, every now and then you'll see this pop up in the past paper, but not as common as I reckon it'll be now for the next few years, right? So there's a trough, right, which is basically like a triangular prism, right, which holds water as it rains, etc. Right, very common now. So let's have a look at it. So this is from Blacktown Boys, 2020, last year's trial paper. So let's say open triangular prism, right, being emptied, right? So it's filled and it's emptying, right? So it's decreasing at a rate of 18,000 centimeters. Once again, what is that? So look at the units, right? Look at the units, centimeters cubed per second. So this guy here is dV on a dt, yeah? Equals to negative 18,000. Negative, right? It's decreasing. So they give you some constants because that's given in the double. To highlight, it's given in the question, right? So 1.5 by 4, triangle end, right? Vertical height of 25 centimeters. Now I wonder, it's a bit misleading how it's 1.5, 4, and then 25. So you know what? Let's be safe. Should I deal with everything in centimeters, right? Everything centimeters. So I'm going to make this 400, right? I'm not going to fall for it. It's 400 centimeters. This guy's 150 centimeters, right? Everything in centimeters, right? Why centimeters? Because the race is all in centimeters, so let's not be fooled, right? Vertical height 25, beautiful. So when the depth of the water is h, the water surface is x, right? So that once again is defining the h and the x, right? Perfect, right? All right. So it's very similar to the cone before, right? We're still going to, it looks like we're still going to use similar triangles, yeah? So let's see. Part 1. Show that the water depth is h. Show that when the water is h, the volume, okay, show the volume, right? Yeah, so I need to find an expression for the water levels, right? Inside there. So, and then part 2, find the rate depth of water is changing. So what are they asked for there? The depth of water is defined as h. So this guy here would be dh dt, question mark, when h is 20. Beautiful. Yeah. So the similar triangles for this one, if you sort of take a cross section, right? You sort of have a picture that looks like this. So I'm gonna, I was using red before, right? So let's do that again. Yeah. So you can see the similar triangles here, right? So let's see, let me draw it in this diagram and then so you got x over here, you got what, 150 on top, you got sort of h being this height here, and then you got 25 being the top here. You just check 1.5. Just looks not to scale. That's all. That 25 looks huge. Well, that 150 doesn't look huge. So I'm hoping I got that right. So let's say, so using similar triangles, right? I'm hoping that I did this right. Let's have a look. 150. Is that right? Let me just check. Yeah, it looks right. It's just the diagram looks just completely not to scale. You're right. It says not to scale. You're right. That's x. So let's see. So I got this guy here is h. I got this guy here is 25, right? So once again, what I say before, small on the large equals this small on the large. So pretty simple there. X on 150 equals to h on 25. Now, I have a question, right? And the question is, which letter do I make the subject? Guys, look at this. The expression that they want, right, has no x's. Feels like I need to make x a subject. Now, before I did actually, let's take a step back. I need to find an expression for the volume, right? This is I'm just doing the water bit down here, right? Just a bit downstairs, where this guy here, that's 400. That's always going to be 400 centimeters. This guy here is h. This guy here is x, right? Just the water bit down here. Yeah? Now, I know that the volume here is equal to base times the height, right? Area of the base times, so that's a half times x times h times 400. Yeah, that's it. That's the volume. Using your year or the year 7, year 8 measurement. Half times 1 is 200, so 200x h, right? Now, can you see, once again, I can't emphasize this enough, that volume expression has x and h on the other side. I don't want x and h. I can't deal with it. I can't do it. I need one letter. So the letter that they want me to get rid of is x, because the volume there is 1200 h squared. I'm going to make x the subject up here. So times the 150 up. What's 150? 125. So that's 6. So therefore, x equals 6h. Guys, copy that down. Take that, plug that into the value of x. 6 times 200 is 1200. Beauty. That times 6h times h, therefore 1200 h squared. How is that? Right, classic. So just like the cone question, right? Exactly the same as the cone question. We had 2 variables, x and h, in the volume statement. Need to get rid of one of them. Similar triangles comes to the rescue and gives us x equals 6h. Sub that in. Got it. Now, I say this always to my students, right? If this was a test, if you couldn't do part 1, if you couldn't do this bit, use v equals to 1200 h squared to do part 2. Don't leave out part 2 just because you can't do part 1, right? So let me put that there. Guys, let's do part 2, where I start by differentiating this guy with respect to t. Right, so bring down the 2, 2400 h, because I'm doing it with respect to h, dh, dt. Right, now, what's the go here? I've got this, haven't I? This is negative, what was it? It's decreasing, isn't it? Negative 1800, huge number. Got h at a point in time, that's 20. And then I know this guy here, right, is question mark. That's what I'm finding, right? I need to find the value of change in height over time. Perfect. And then it's just literally subbing in numbers, right? This shouldn't be hard. Times 20, saying that, watch me do a mistake. Always do this. Yeah, I believe if you punch that in, make dh, dt the subject, I believe you get what's divided all over negative 3/8 or something, 0.375. What's the unit? Centimeters per second. Yeah, or you can say that it's decreasing at that rate. Guys, how's that? Yeah, has this question, it's a classic, right? So it's slowly becoming a classic. It's in a lot of, it's got a lot of exposure. Cambridge likes to deal with it. Past papers now pull it up. Hopefully that's okay. Yeah, guys, one more question. Yeah, the next one is nice because it leads me on to next lesson's method using implicit differentiation. Now, so whenever you deal with a question that looks like this, where the relationship between the variables is Pythagoras, right? You can do it by the method I'm going to show you today, and then I'm going to also allude to the implicit differentiation method next week. So let's see. In this question, you have the weather balloon, right? And it's rising vertically, right? So the weather balloon's here, it's rising, right? That's the rise at that. Why is that important? Because this is the rate that it's increasing at upwards. It's the change in the vertical height, which is a change in h. This guy is dh dt 5. Yeah? That's important. Yeah? An observer is standing 300 meters. So this is fact. As given, that 300 is never going to change, right? Always saying. So you can imagine if this was a balloon here. Yeah, I need for a balloon. There you go, something like that, right? It's going to go up and up and up, right? It's going to go up and up and up. The only thing that really changes is this arm and this arm, right? That's the blue line on the bottom doesn't change. It's fixed. Yeah, good. I'll leave the balloon there. It's nice. Get rid of that error. Where the balloon is at, let h be vertical height. X is the distance between the observer and balloon, right? You can see the connection between the three sides. Wrong tool is Pythagoras. Yeah, all to do with Pythagoras. That's why that looks a bit Pythagorean. Yeah, Pythagorean. All right, show that x equals that. Beautiful. Is Pythagoras and square root it. Piece of cake. At what rate is the distance between the observer and the balloon changing? So that's this distance here. So this is dx dt equals a question mark when the balloon is 400 meters high. So 400 meters high vertically, should have really said, h is 400. Yeah, so it feels like if this is like you know, in the past questions, this guy here is like my volume expression. Yeah, I'm going to prove that and then differentiate that with respect to time and then sub in my stuff. Right? Pretty sweet. So part one. Yeah, I have, once again, I'll use red here. I have a right angle triangle, and I'm just gonna simply apply Pythagoras' theorem to it. 300 meters, whereby x squared equals to h squared plus 300 squared. Yeah, Pythag. And then, yeah, therefore, x is a distance, is always going to be positive. H squared plus that is 90,000. I mean, too many zeros. That's it. That's one mark. Piece of cake, right? Yeah, nothing too fancy about that. Yep. The next bit's a bit fancy. So let's see. Part two. I want the rate of change of the distance between the observer and balloon, so dx dt. So I'm going to differentiate this guy with respect to time, so dx dt. Now, guys, hopefully you can actually differentiate this guy here, right? This expression here, differentiate. So that's like, if I was to rewrite that with in the index form, h squared plus 90,000, power of a half. Apply the chain rule there where you bring down the half, right, to differentiate. Yeah, take away 1 from that power, and then multiply by the derivative of the inside, which is 2h. Chain rule. So let's clean this up a little numerically. So the 2's cancel out. I always say to my students, 3 things happen. The 2's cancel out. The negative power goes downstairs. The power of half becomes a square root again. Yeah. So the only thing that's left upstairs, so if I go dx, chain rule with respect to time as well. So times dh dt. I forgot about that. Raise the change, right? Please remember that. Now, let's clean this up before I sub in my stuff. So then what do I have here? dx dt equals to, so the 2's are gone. The only thing that's upstairs is a h. Bring this bracket down, get rid of that negative and turn it into a square root. So a couple of steps there, 3 steps, right? In one. And multiply by dh dt, perfect. That's a hard bit, because now it's, well, really the straightforward bit where I basically say to myself, well, they gave me in the question dx, oh, no, they didn't give me that. They gave me dx, dh dt rather. That's 5. That's it. H is what, 400. So let me go down here. H is 400. Yeah. That's it. Sub everything in. Therefore, dx dt equals 2. I think it's a nice number actually, because I think that's 400. That's like nice, but that's if they're under 400, that's 500 then, surely. Times 5, 4 and 5 times 5, 5, 4, right? Therefore, dx dt is 4 meters, seconds per second. Yep, per second. That's my answer. So guys, a little bit different because of Pythagoras, and I guess the hardest bit in this question is not actually Pythagoras, but it's the differentiating the expression that has a square root in it. But same concept. Now, next week, next lesson, we're going to explore this question using implicit differentiation. Usually done in 3 unit, but you know, it's a cool little technique. Happy for you to learn it, and for those that want to apply it in advance, you know, ask your teacher and see if you can. hopefully that video is good. If you liked it, please give me a like, subscribe, tell your friends, and work the YouTube algorithm. I'll see you guys at the next lesson. See you later.